I'm Brian Diaper from the Embedded Vision Alliance. I'm your moderator for at least most of this afternoon's talks. Quick reminder, please to continue filling out your surveys throughout the day while your thoughts about the various presenters are still fresh in your minds. Speaking of presenters, I know this guy, I've known him for a while. I've actually videotaped this guy in action, delivering a number of demos for his company. So if you'd like to see him in action for yourself, go to the Lattice booth afterwards, and he'll do them for you personally. And you can find out more information at that time as well. Sandeep, Hussein Osman currently manages the consumer segment at Lattice. His responsibilities include driving integration of Lattice products and solutions in his consumer products, like mobile devices, wearables, and IoT devices. You just yesterday or a couple of days ago announced an update, press release regarding the products that you're going to be talking about today. Yeah, excellent. So he's going to show in this talk why Lattice's low-power FPGA devices, coupled with the sensAI software stack that I just alluded to, are a compelling solution for implementing sophisticated AI capabilities into edge devices. Hussein?
Thank you.
You're welcome.
All right. Hello, everybody. Hope you enjoyed your lunch. So what I want to talk about today is how low-power FPGAs are enabling AI at the edge. So I tried to strike a balance on my presentation between getting too technical or just talking about marketing stuff. So if you have additional questions after the talk, come to our booth 205. You can't miss it. It's right up front as you walk into the building. And I have some of the technical guys to get into the details there. So let's get going. So first, I want to start by talking about how we define the edge. So depending on who you talk to, the edge are different things. So for us, the edge is everything on the left-hand side of that slide. So wearables, drones, I call them IoT devices. So anything on the left-hand side there is something that we want to focus on. And Lattice believe we have the right solution to enable AI on this type of devices. And so what kind of applications are part of the applications are that defined by that edge? The applications are something like human control or human presence detection in a house. So our sensors can stand alone in a house and detect if somebody's falling. It can be used for building control in a house, gesture detection for human to machine interface, voice detection for similar applications. On the bottom left corner for industrial applications. So one of the demos we're showing here is defect tracking or defect ability to check defects in a factory environment. On the right top corner is security cameras and doorbells. These are items that we have solutions that fits into these items. So retail stores somewhere also work very well for inventory tracking and for detecting who's standing in queue, for example. So let's get more into it. What's common between all these applications is some of them require very low power implementations. Okay, some of them require small size. Some of them require ability to customize it based on accuracy versus performance versus power. So FPGAs have ability to cover all of these areas, and Lattice FPGAs especially are designed in such a way that they're a good fit for AI at the edge, and I'll discuss more about that. One of the ways we are good at this is the fact that we have very flexible IOs. FPGAs just they're used for bridging, in general. So we have I2C, SPI, Ethernet, PCIe, any interface that it can digitally be put into a LUT inside the FPGA, we can emulate and we can do it. Okay? So what have we done to enable AI at the edge? We went out and we created a solution stack. This solution stack is made out of hardware platform all the way in the bottom. The solution stack is actually, let me start by first saying it's around 2 FPGA families that we have. The ICE40 Ultra Plus is on the left-hand side, and the ECP5 on the right-hand side. So if you go up vertically from the left-hand side on ICE40 Ultra Plus, you see that there is a hardware platform that enables you to prototype our solutions. On top of that, there is CNN accelerators that are optimized for this device. On top of that, there's software tools, and there's 2 tools, and I'll explain how each one of them is used in the next few slides. But Radiant is one tool we use for FPGA, RTL, and putting a design into an FPGA. And then we have a neural network compiler that helps with training and taking trained quantized weights and activations into the device. Then we went out and we created a bunch of reference designs that are going after some of these areas that I talked about in the beginning, smart doorbells, factory automation type of applications. And we also know that a lot of users don't know AI, and they don't know FPGAs. So we created a bunch of partners that know AI, know FPGAs, and can help some of these customers get to production. On the right-hand side is the same stack, just around ECP5. ECP5 is our higher-end FPGA, and I'll talk more about it. And we have a CNN accelerator that runs on ECP5. And we have software tool, Radiant, that enables you to load a design into an ECP5. And then demos such as speed sign detection, object counting, face tracking. Object counting is a generic reference design, can be used to train for any object of interest. So with this stack, I want to get a little bit more into why Lattice FPGAs are good, or what makes them a good accelerator. So here I'm comparing Lattice FPGAs to other solutions in the market in this area. So the ICE40 Ultra Plus, this device in a CNN mode has about half a GOP, and it has up to 5 GOPs in BNN mode, okay? An ECP5 is also about 512 GOPs in BNN mode, or about 30 GOPs in CNN mode. We're not going after the server market. We're not going after areas where GPUs and ASICs are going after. We think at the edge there is a need for smart devices to enable many applications, and I gave you some of these applications. And our solution is, I use this analogy a lot. There are certain problems, like I say, if you're commuting, you don't want to bring a Hummer to your commute. You want to bring a Honda Civic. So, these type of devices are optimized for these problems. So first, I'll start with the ICE family. The ICE family has up to 5K LUT. This is the slice of logic that's programmable within the device. It has a 1 megabit of SRAM, perfectly suited for AI applications. It has flexible IOs. It's a low-power implementation. And it turned out the way Lattice designed our FPGA, there is a slice of memory, a slice of DSP, and a slice of logic. So today's ASICs that are being designed for this area are being designed exactly that way. And we just happened to design FPGAs in this way prior to even this whole AI area coming out. So again, in the bottom, it talks about performance, about half a GOP for this ICE40 Ultra Plus, and in a CNN mode and BNN mode, about 5 GOPs or so. Next, I'll talk about the ECP5, and we call it the low-power AI accelerator. It comes in packages as small as 10 by 10. And I'll go back to ICE for a second. ICE comes in a package that's 5.5 mm squared. So about a GOP in 5.5 mm squared, a gigahertz processor in 5.5 mm squared. So back to ECP5, 10 by 10 package, automotive grade certified, so you can take it for automotive solution. Performance up to 32 GOPs in CNN and 512 GOP in BNN mode. Okay, we support 1 to 16-bit activation, and today we support 1 and 16-bit weights. we're working on 8-bit activation, which is going to be our next release, pushing our performance even further. ECP5 has SerDes, so you can have a PCIe interface to an MCU, making ECP5 sit in a system where MCU does not have to have the acceleration within it, and just push the data out to our device and let it do all the acceleration through a very fast link. Okay, so 1 watt, 850 milliwatt for most applications. Next, I just want to tell you a little bit about what areas we see our customers, or how our customers are using our solutions. So there are 3 use modes that we see. A standalone sensor, so our device sits next to the sensor, grabs some data, analyze it, and maybe send an alert when needed. Okay. Pre-processing, so in the pre-processing mode, our ICE40 Ultra Plus sits next to the sensor, grabs data, and when a specific event happens, triggers a more power-hungry rest of the system to do further analysis, and this could include cloud. Another pre-processing scenario, a lot of our customers have an MCU already in their system. They don't want to change the MCU. They don't want to change the architecture. They like how things are bug-free, but they want to add AI acceleration. They can drop our device next to their MCU, and through a SPI interface or something like that, we can provide them results for specific patterns that are coming from a sensor. Okay? Post-processing, and this is how it's used in a lot of smart doorbells. Smart doorbells need to work across all kinds of lighting conditions, for example. So we take the data from an image sensor, bring it into an ASSP that does cleaning up, and then passes on to us a frame, and we'll look through this frame for a specific pattern that the system was trained for. So the 2 next slides are just for reference. These are our IP cores. This is our CNN IP core for ICE40 Ultra Plus, and you can see some of the blocks that are in there. This slide is up on our website. You can look into the details, and you can come and talk to me about it after the talk here. And next one is the full CNN IP core. This is for ECP5, the bigger device that we have. And again, weights 1 16-bit, activations 1 8 and 16-bit. So another piece I talked about a little bit earlier is a neural network compiler. A neural network compiler is a translation tool that takes the output of mostly the machine learning tools that are most used, Caffe, TensorFlow, Keras, and takes those weights and activation and makes them into a bin file that interacts with our CNN IP inside the FPGA. And this is a seamless way that we thought of, doing the translation between the training tool and our FPGA. And some of the improvement that we announced on Monday went into this part, into the software tool. So what improvement have we done recently? So we introduced the sensAI stack about a year ago here, and we're coming back a year later with 10x performance. So the aspects of improvement is performance and user experience. Performance, 10x improvement. So 10x in terms of what? In terms of speed frames per second. We're able to do much higher frames per second. So up to 30 frames per second with a VGG, for example, running on our device. We are also able to do higher resolution. We have our examples running at 256 by 256 on our FPGA. This means that you can go run the same neural network on a smaller device. The ECP5 family of devices has an 85K LUT, 25K LUT, and a 45K LUT, and 25K LUT. So the same neural network that you're running on an 85, you can go run it on a 45 now and get a lower cost, and so scaling across our portfolio of FPGAs. And same way, by lower power, because you can move now to ICE and smaller devices. Okay, so this is the other aspect from a user experience point of view. We expanded the list of neural network topologies we support. We introduced hardware debugging capabilities. We made quantization, which seems to be a pain to a lot of people. We made it basically seamless and automatic. And we put out a bunch of demos and reference design that has all the right pieces in order to get somebody into production. And I'll talk about that in a little bit in detail. So for our reference designs, we give you neural network models. We give you the training data set, a sample training data set that's being labeled the way that we believe data set should work with our devices, and a training script. You have all pieces for training. You can take that into Caffe or TensorFlow or Keras, and then output of that into the neural network compiler, and then into our device as a bin file. In the bottom side of things, that's the traditional FPGA methodology, and there we give you the neural network IP, and we give you interface to sensors. Speaking of sensors, our device doesn't care what sensors we're taking in, IR sensor, a image sensor, or anything else. I know this is a vision show, so I'll keep it to that. So customizable reference design has all the pieces. And a lot of the users that we talk to just don't know too much about AI. We felt like we need to give them everything that they need in order to go to production with this type of solution. So we created these demos. These demos can be taken into production as is. So the human presence detection on the left-hand side runs on IS-40 Ultra Plus. The input is an image sensor, a 64 by 64 by 3 into a VGG8 network. And this runs at 7 milliwatts. So this is the gigahertz processor in a 5.5 mm square that I talked about previously. On the right-hand side is the human counting. So you can do binary detection of a person or no person, or you can count the number of people in the room and where are they located exactly. And that's our higher-end FPGA. 128 by 128 in this demo. We have other demos in 224 by 224 by 3 on a VGG8, running 30 frames per second and consuming 850 milliwatts. So we believe our products are very differentiated and targeting a specific area of the market that nobody else is targeting, or if they're targeting it, they have an oversized solution for that area. We also expanded the number of design partners that we have. We have added about 5 more design partners. Most notably is on the right-hand side, Pixelance. Pixelance is a company that does products. So they took our solution. They have an ASSP that does light cleaning up or image cleaning, and they're able to use us as an accelerator in their system. Any of these customers, including our internal support teams, are able to help users or developers take product into production. So just coming to an end here, some of the awards that we've won with the sensAI stack. Just wanted to note that. And finally, if you have any questions or more details you want to know about our stack, come to our booth, 205 in the front of the building.
Applause for our presenter. Nice job.
Thank you.
Thank you. So I'll direct your attention to the mics in the center of the room for any comments or questions that you have. As usual, I will start with one.
Okay.
What layers of a typical deep learning model do you typically recommend could be accelerated and processed in your chips and via the associated software? And does that depend on the product and the product line? You talk about 2 different ones here.
Yeah. So it doesn't depend on the product line. Across product lines, we support ReLU, we support batch normalization, pooling, and convolution. 3x3 convolution, and we're working on 1x1 convolution. And I notice other solutions don't even expose these things. They just give you a CAN solution and say, go use it as is. We're exposing this because we want to give additional ability for people to play with these. And we keep adding more and more structures as we go forward.
And would the rest of the layers typically be done on a host processor?
It can be done on a host processor.
Okay.
So you can split the network, but these are what, with sensAI, we support today. These are the layers that we can.
So how does the software handle that subdivision of the total processing task?
So at this point, we're mainly used as the full accelerator, and we're just passed on a sensor data in terms of an image, let's say 224 by 224, and saying, hey, look for a specific pattern within this image. And what the host does as pre-processing to that it depends on the system that's being used.
I said one question. I guess I got three in there. Sorry about that. All right. Any comments or questions from the audience? Anyone? Going once? Going twice? Okay. Thank you very much. It's break time.